Now on to chapter 13, so like that. So this is nuclear magnetic resonance spectroscopy, so like that. So this is actually the basis for, or I should say, for things like MRIs, like that. So if you go in and have the big tube, put your head in if they want to check it out, so like that. So this is actually the same technology that's used for that, like that. So I will warn you that this is probably one of the stranger topics we'll deal with, so like that. But the key thing is the fact that it's really just about problem solving, right? So it's these sort of problems of Tom can't sit next to Jan, but Jan likes to sit next to Bobby, and Bobby can't stand Timmy, and that sort of stuff. And so how do you put all the little parts together in order to be able to satisfy what we're seeing? So like that, there's really going to be only one solution for all of this. So like that, what you need to do is be able to figure this stuff out. But the first part is going to be a lot of background. Then we'll start dealing with carbon atoms, and then we'll deal with hydrogen atoms. So like that. But this is the primary way that that chemists will look at structure, right? So to be able to figure out the framework for how the carbons are all put together, right? So this way you can you can see the actual structure by putting this all into place like that. So what we're going to be doing is we're actually going to be looking at the nucleus of the of the different atoms. So the nucleus, right inside, you've got positive charge, right? It's going to be spinning, right? So anytime you have a spinning positive charge, you're going to have a magnetic field. And normally they're just sort of going wherever. They're sort of randomly positioned, something like that. But once you put them in a strong magnetic field, in this case inside of an NMR, which is a superconducting magnet, they actually align. The magnetic fields will align either with the magnetic field or opposing it. So it's sort of a, so the idea of saying this is sort of sheep wandering around, a field, right? Because they can go wherever they want. But if you're talking about like a school of fish, right, the easiest way to travel, right, is either upstream or downstream. Something like that. So I should say upstream, downstream. If the magnetic field's there, right? So you're going to go up and down, right? They're going to align with it. Okay, and we're going to take advantage of this alignment within this magnetic field. Okay, because what's going to happen is we're going to be able to put in energy. In this case, it's going to be radio waves. And basically, what we want to do is we want to see how much energy it takes, right, to flip it from going downstream up to upstream, right? So that's going with the magnetic field to against it, right? So that, and this gap we can measure, right, how much energy it puts in there. And the stronger the magnetic field, the harder it's going to be to go upstream, right? So you sort of think about, the faster that river is traveling, right, the harder it is going to be to go from downhill to turn around and go back upstream, right? So like that. So it's the same sort of thing, right? The stronger the magnetic field, the bigger this gap, right? The harder it's going to be, but we can measure this energy, okay? So and depending on what the environment is going to be, right, we can measure that. Okay, but the big thing is how if we're going to be flipping the magnetic field of the nucleus. Okay, and so the problem is only some nuclei are magnetic. Okay, you would think that they're all, but not all of them are. And it turns out that if you have either an odd number of protons or an odd number of neutrons, you're magnetic. Okay, it doesn't matter which one, as long as one of them solves it, you're good, right? So with that, but if the atoms have both even protons and even neutrons, right? So with that, then they're non-magnetic. Okay, so in this case, right? With that, so if you look at your right, so look at the periodic table, right? If you're looking at something like, I don't know why I got that. Right, so if you have a hydrogen 1, right? So this number, right, is neutrons, right, plus protons, right? And this understood number down here, which is a smaller number on the periodic table, that's just the number of protons, right? That's what defines what the atom is the number of protons here, right? So in this case, right, so we have hydrogen is equal to 1 proton. Well, boom, we have a negative, or excuse me, an odd number of protons, it's automatically magnetic. Okay? If you look at something like carbon-13, right? So again, carbon is what? It's carbon. It has 6 protons to it, right? 6, right? So like that. So this one is neutrons plus protons, right? Right, it's equal to 13, right? So if this is 6, right, that means that this is 7, right? This is odd, so we're good, right? That's odd, okay? So you do that for all of them, right? So for 19, right? So, right? So I'm sorry, 19, nitrogen, right? So we have 14, right? So this is neutrons plus protons, right? Equal 14. But how many protons does a nitrogen have? It has 7, right? Because it's in the 7th position, right? So like that. So this is odd, right? So we don't have to worry about this, right? So that's odd. So this is magnetic, right? No problem, right? But the problem is for something like carbon-12. Okay, carbon, right? It has six protons, right? So neutrons plus protons, right? Equal to 12, right? So if this is 6, right? We know that because it's the number of protons. It's a small number on the periodic table, right? How many neutrons does it have? Well, it's got to have 6, right? 6 plus 6 equals 12, right? So these are both even, right? So that means it's non-magnetic. Same goes with oxygen, same goes with sulfur, right? Just because the upper number is even doesn't necessarily mean that it's non-magnetic, right? You have to look at the number of, if either the protons, right, or the neutrons are odd, you're good, right? Because you can get an even number either by adding 2 evens, or you can get an even number by adding 2 odds, right? So like that. So, okay, so just because this upper number is even doesn't necessarily mean anything, right? So like that. So this is a good thing to remember, right? So, but the problem is, right, carbon-12 makes up most of it, right? So we're not going to be able to take advantage of carbon-12. But we are going to be able to take advantage of regular hydrogen, so that's good. So, we're part of the way there. So like that. So, okay, and so what we're actually doing is we're actually looking at what really is the signal that comes out for the individual nucleus is actually what the effective nuclear field is. We know what we apply, right, because it's going to be the same, right? But the local environment is going to change what that nucleus is feeling at that point, okay? And so it's going to change it ever so slightly, right? The spinning of the electron fields, the neighbors, right? But what's attached to it. Okay, that's going to change the field. It's either going to make it feel more or less, right? So it's cold out. It's been cold this weekend, right? So if you can have it where it's the difference between walking outside with a heavy coat. You don't feel the cold very much, right? So with that, so if you walk out with just a t-shirt on, right, you're going to feel it. Right? You're going to feel that magnetic field. You're going to feel that cold, just like removing electrons around here are going to make that nucleus feel the magnetic charge more. Okay, so with that, so what we're really looking at is these small differences in the shielding around this nucleus. How shielded is it towards that effect? The magnetic field we put in there, and that's what we're looking at. Okay, right. So with that, and what we'll see is we're going to see these peaks here. Okay, so from the different spectrum. We typically put in an internal standard, which is trimethylsilane, okay, which we set as 0, okay. And so the reason why we use this one is it's far enough. We'll find this later. It's what upfield. It's far enough out of the way. It's far enough to the left, or excuse me, to the right here, that it basically stays out of the regular signals, right? So that we don't have to try to find this. There's a whole bunch of signals in here. We don't have to find the TMS signal somewhere in there. It's far enough out to the right that it stays out of the way. But we're going to set that. We just add a drop of that to our solvent, right? It's a fairly big signal, right? And so if we're looking at either hydrogen, we'll talk about this carbon-13 NMR, right? We see that we can use the same standard for both. Okay, but we're going to see signals for the difference in this case for hydrogens, right? So we can only look at them one at a time. So hydrogen NMRs only looking at the hydrogens. The carbon NMRs only looking at the carbons, right? So this is one signal. You have to go in, reprogram it, the NMR, and then run a different experiment to do this one, to do the carbon NMR, right? So you have to do them one at a time. Okay, so with that, but each of these each of these different carbons, right, are going to have a signal. Each of these hydrogens are going to have a signal. in the NMR. Okay? Okay, so how does this work? Okay, so the you actually put it in the sample. I actually have one here. You put it in a little tube. Okay, it's a long tube, but you only need to fill up maybe about that much, stuff like that. So, but it's perfectly straight. It's kind of hard to see, but the tube is perfectly straight because it's going to spin. Right, it's going to spin in the sample. It's going to spin quite fast, right? And if it wasn't perfectly straight, it would wobble, and that would throw off your signal, stuff like that. So it's a little tube like this. Stuff like that. So you put it in a big machine. I'll show you what the machine looks like. You put it in the center of this giant magnet. Okay, and then inside it spins, and you put in this radio frequency generator. It pulses in different frequencies of different radio waves, and out behind it we get a detector, and we see and we see the signals that come out. Okay, we see what's absorbed and what's not. Okay, so with that, and so typical NMR strengths are actually they're given either two different ways. They're either given as the actual magnet strength, okay, in Tesla, but more commonly it's given in the strengths of what are called megahertz. Okay, and this is typically what you're doing, but it's the same thing: small number, small magnetic field, big number, big magnetic field. Okay, so about that. So they typically look like this. So this is a 200 megahertz NMR. It's fairly small. You can sort of tell from the little step stool here. It's probably, I don't know, 3 or 4 feet, or excuse me, maybe 4 feet tall. So like that. So not too bad. Like that. So inside of here is a superconducting magnet that's sitting inside of a pool of liquid helium, and then outside of that is jacketed by a pool of liquid nitrogen. Your sample goes right in, right where that red part is, there, stuff like that. So you can also, for a higher field strength, right? So it sort of looks like an R2D2. For a large magnet here, so this is a 900 megahertz. This is a Bruker. So you actually have to you actually have to have these platforms you walk up, and you put that same signal or that same sample inside of the top here. And actually, lots of times now they have sample auto samplers, which you just put it down here, a little robot grabs it, puts it in, stuff like that. So, but these things are pretty expensive. So it used to be, for every, what was it? It was 1,000. Basically, you can sort of take this number and add 3 zeros at the end, and that's how many dollars it is. So like a 200 megahertz would be $200,000, and a 900 would be like $1 million. But it turns out that one of the competitors went out, stuff like that. So Varian went out, so now it's Bruker and Joule, and Bruker raised up their rates, and so right now the sweet spot is sort of like a 400, which runs roughly 300,000, I think it is, something like that, dollars. But if you went up to say a 600, you're talking, depending on the supplier, anywhere between 600,000 or 800,000 all the way up to 1.2 million, stuff like that. So these are pretty expensive. I can't imagine how much the 900 is. Probably 5 million, something like that. The gigahertz one that just came out, I don't know how much that would be. It's pretty expensive, stuff like that. So why do we care? Oh well. Also before that, so the nature of the absorptions. Okay, the NMR is actually very, very slow. Okay, so like that, and so it's very slow in the relative to how fast these molecules are wiggling around, right? So remember the chair structure, they're sort of going back and forth, right? So like that, and so it can't really tell, so it's blurs, right? So it can't really tell, right? So you have the axial and the equatorial hydrogens here, right? Here and here. So it's wiggling back and forth, right? So when you do the chair flip, right, that becomes equatorial, that becomes axial, and when chair flip backs, right, it goes back, right? So like that. So it can't tell, it's going too fast. If you want to figure out that these two guys are different, what you have to do is you have to slow down the wiggling, right? So like that, you have to slow down the chair flipping. The easiest way to do that, right, is to cool it down, right? So if you cool it down, so the chair flipping, instead of going, back and forth fast relative to the NMR, you just make it slow, right? And slow enough that, that it can see the individual pieces as opposed to blurring it out. So if you want to see something, you want to see the individual hydrogens, if you think that they're there, so what you have to do is you have to slow it down and see if the spectrum changes. Okay, chemical shifts. Okay, so this is where we're talking about how, sort of where these sort of subtle differences between with the local environment. Okay, so like that. So what we see is actually just some terminology. If it's to the right, okay, we call that upfield. Okay, that means it's shielded. It doesn't feel the magnetic field very much. Down here, towards the larger numbers on the left, it's called downfield. Okay, so with that, so it sort of goes down that way. I don't know why. It's just been tradition. I think there's probably. I think I know why it goes. It doesn't go 0 to 10, right, like it normally was. But I think it was probably the early instruments. They would have a pen and they would have these and they would draw it out individually. Now it's all done on computers, so you don't have to worry about it. But I think the first instruments did it like this, and so they just kind of stuck with it. But anyway, but deshielded is downfield, shielded is upfield, and it's over here. The calibration peak is usually set at 0, so ppm. Okay, so how do you calculate this? It's the hertz from the TMS signal. How far away from the TMS signal is it? Okay, relative to the strength of the NMR. Okay, and this is nice, the fact that we're making it relative to the NMR strength, because that means it doesn't matter which, if you have the 200 or 900 NMR, if you have a 2.3 ppm signal, it's going to be 2.3 in both of these NMR. You don't have to account for it. The way that the numbers are put together, it takes that into account. I'm not going to make you calculate this, but this is what's going on. So how far away in hertz, right? So hertz, right? The wavelength of that is absorbed relative to that TMS signal, divided by the megahertz signal of the NMR. Okay, and something over 1,000,000, right? That's where we get the hertz per million from. So hertz over megahertz, 1 over 1,000,000 ppm. Okay, so with that, so why do we need these big NMRs, right? Even though they're millions of dollars. Okay, well, it turns out that it's just all about greater resolution, right? So with that, so if you have a difference between two hydrogens, two signals, that's 1 hertz, right? You're going to need the difference between at a 200 megahertz is 0.005 ppm at 2, and about 1.001 ppm, right? So you get much higher resolution. And the easiest thing to think about sort of real life is the difference between a 2 megapixel and 9 megapixel camera. Right? You're going to get much higher resolution. You can zoom in closer and still see good things, right? So in a 9 pixel as opposed to a 2 megapixel camera. It's the exact same concept. Okay? Stuff like that. So okay, so the reason why it says for a simple signal it's not a big deal, but if you have a complicated signal like a proton or a protein, right, you're going to want it, right? You're going to have a lot of differences, a lot of peaks, right? And so getting that higher resolution is important. So a lot of these samples, what are done on NMR, these complex molecules like proteins, polymers, things like that, other sorts of big molecules. That's what these things are used for. So, okay, so chemical shifts. Okay, and so that's what's going on here. So, okay, so the first one we're going to talk about is carbon-13 NMR. So like that. And so this one here is, remember, we cannot use carbon-12, right? Because carbon-12 is not magnetic, right? So what we have to do is we have to take advantage of this sort of 1% isotope of carbon-13, which is magnetic. Okay, so you're only going to get 1% of the signal out of there, right? So with that, so you have to sort of play with this, right? Because so only 1 in 100 carbons are actually going to give any sort of signal, right? So you have to play with this. And so what you do is so to get a good signal, how do we do it, right? So with that, so what we do is we do signal averaging, right? So and plus Fourier transform, which is a magnetic, so with that, so the manipulation of it. Okay, and then we have to take a lot of sample, or a lot of we have to sample it a lot, so like that. So lots of times what we'll do is this will take minutes to hours. If you have a kind of complex signal, what you can do is you can set it up and let it go overnight, let it go for a few hours, and let it go run overnight, so like that. So that works pretty well. Okay, so what happens is, right, so if you take one signal, right, if you take one pulse, this is the sample that you get, right? But it's really hard to tell, is that a real signal? What about these guys? You know, which of these are real signals and which is just random noise, right? But if you take 200 and then average them, right, so like that. So these guys here, the actual signal are going to be always additive, right? These guys here are noise, and so they're going to go back and forth, right? So the easiest way to think about these is that for with random noise, you sort of think about a coin flip, right? So like that. So you say, okay, right? So at the right. So if, let's say heads, you win $1, you know, or you get a point. I should say this: you win a point, and then if it's tails, I win a point. Okay, and so if we flip it, 200 times, right? So with that, assuming we have a fair coin, right? What's on average? What's it going to be? It's going to be, you know, you have 100 points, I have 100 points, and so it's going to be a tie. And so, right? So it's all going to basically average out to 0. Okay, of who nobody's going to get a big lead, right? Stuff like that. So okay, so nobody, in theory, nobody could get a lead. Okay, but for these, we can say, okay, you know, for an actual signal, right, what would happen is, you know, heads, you get a point, tails, I don't get anything, okay? And so what's going to happen is this is constantly added, right? So after 200 signals, or 200 flips, right, you're going to have 200 points, I'm not going to have any, right? And so then it's going to get a really big lead, right, which it's a really big signal. Okay, so random noise is eventually going to go to 0, but the actual signals are going to keep adding, be additive, and eventually they'll grow in and grow well above the noise, right? Because if it's just noise, it's just going to go away. Okay. Chemical shifts. Okay, so it turns out that right, we've been saying this local environment is going to affect where this is, and there's some fingerprint regions for where these things are. Now, here's this. Right, so you can look at sort of a standard array of chemical shifts, right? So regular CH3s are sort of in here. If it's sort of 0 to 50, you know, just regular carbon, you know, with just hydrogens attached. If it has something electronegative on it, right? So either halide, or nitrogen, or oxygen, it's probably going to be somewhere between 20 and 80. Okay, and so these signals, they're not absolutes. It's sort of a general sort of, yeah, that's probably where they're going to be. If it's attached to an oxygen, right? So it's probably 60 or 80, but it could be 55. It could be 85. Who knows? Stuff like that. So, right. So if you have an alkyne, right? So C triple bond C, it's going to be sort of between 80 and 100, which is interesting because the C double bond, right, is actually up here at sort of 120 to 140, along with the aromatic, along with the C triple bond N. So that's sort of very characteristic. And if you have a C double bond O, right, so a carbonyl group, it's going to be way, way downfield, right? Sort of north, you know, so higher than say 160 to 220, 250, 240, somewhere in there. Okay, and so by that, so a lot of the sort of stuff is going to end up here, right? But as you get more electronegative stuff on it, it's going to be shifted further downfield. Okay, so we can take advantage of that. Where these, not just what the signals are saying, but where they occur is going to be important. Okay? Okay, and so the characteristics of these, and we'll talk about being able to assign these. Okay, so by that, and so right, so the C4, right, so that's a regular CH3, which would be here, right? This CH3 again is over here, right? Because CH3s are typically right around there. The number 2, which is C double bond O, it's going to be sort of up, you know, sort of up in this region here, and in this case it's 208, right? So about that, so which is where we expect. And this guy here, the CH2, right, is here because CH2s are typically a little bit more downfield than CH3s are. So about that, so there we go. Okay, so for here, we actually have, in this case, right, so if you spin that, you know, just hold this and this together, right, you can sort of spin it, right, and this, the 4 and the 4 prime would be in the same place if you held onto these two. All right, so these guys here, there's only 4 signals, right, 1, 2, 3, 4, right, because there's only 4 equivalent, because there's 4 equivalent carbons, right, the 4 and the 4 prime are actually the same, right, they're 1 away from being attached to this ketone group and 2 away from the bromine, right? So they're feeling it the exact same thing. These 5, the ones at 5 and 5 prime, which are down here, which are down there, right? So with that, so that is 1 away from the bromine, right, and then 2 away from the ketone here. So with that, so they're going to feel the effects the exact same way. Okay, so with that, so we'll talk about right, and that acetyl bond O is here, right, where you would carbon number 2, which is acetyl bond O, is here, right where you expect it. These ones in the benzene ring, they're part of the aromatic, they're right here where you expect it. Right, so that the CH3, which is sort of near the acetyl bond O, it's right here. It's been shifted down a little bit further, right? So with that, from where you would expect, because it's something next to something that's relatively electronegative. So with that, so that sort of shifts it down a little bit, but it's right in the region we would expect. So okay, so again, you can assign these peaks based on these, right? So with that, so right. So with that, so here we go. Right, so we have a peak at, right, we have a peak about 10, right, we have a peak about 25, right? We have a peak about say 52, and a peak at say 175. Okay, so if you look at the chemical shift table for these guys, okay, hopefully you can see this, right? So okay, so this one here, the 10. Hopefully I get these right. So right, so this CH3, right? So that's right about where you would expect it, right? So this is probably going to be the 10 here, okay, because it's sort of what's next to it. It's another CH2. That's probably it. Again, that CH2 is probably going to be right, sort of like so. Right, the CH2 here is probably going to be right around 40. So it might be this one, might be this one right here. But this CH3, right? Notice how it's attached to an O here. That usually comes down in this region here, right, which is shifted a little bit downfield. Okay, and so this one here is probably going to be the 52, right, because it's attached to that. It has that O attached to it here, right? That has that O. Okay, and then this guy here, which means that this guy here is probably the 25, right? And then this one's easy, right, because the 175, they're always going to be in way downfield here, right? So it's a 175 there. How'd I do? So number 1. Right, so which would be here. So this is right. So this is number 1, number 2, right, number 3, number 4, right. So there you go. So 1, right, 1, 2, 3, 4, right, 1, 2, 3, 4, right, something like that. So just as we expected. Okay, so like that. So. Okay, so the other thing we're going to talk about is, so that's, you can do this, right, if you sort of simple molecules, but when the molecules get big, you're going to have to get a little bit more creative, okay, stuff like that. And so what we do is we turn to this, what's called depth, stuff like that. So it's distortionless enhancement by polarization transfer. I know what you really know. I just know it as depth, okay? And so what happens is you can assign the, what's a C, what's a CH, what's a CH2, what's a CH3. That's the whole point of this, okay? And so what will happen is you'll get 3 signals out. You'll get a regular one where it's just decoupled, so you just get all the signals, okay? For depth 90, it only shows CH. That's the only thing it shows. If it shows up in a CH, that's it, okay? Now, depth 135, you'll get two types of signals. You'll get a positive signal, okay, and you get a negative signal. Okay, so like that. So the positive signal would be CH3, so the odd-numbered ones, but the CH2 will appear negative. Okay, and so what happens is if it's in the depth 90, right? So you can say, well, how does it? And then the quaternary ones, right, don't appear at all. Okay, so like that. And so you can say, like, well, okay, so the CH2s are easy to figure out because they're the only ones that won't go negative. Right? So how do we tell between if we get a positive 135, if it's a CH or a CH3? Well, if it's a CH, it'll also appear up here in the depth 90. Okay, so if it's in both of these, right, it'll appear it's a CH. If it's negative, it's a CH2. If it appears only in the 135, it's a CH3. And if it doesn't appear in the 90 or the 135, right, it only doesn't in the decoupled, then it's a quaternary. Okay, and so those are that's how this works. Okay, and so if you have this molecule here, right, so hopefully you can see this a little bit better. Right, so this molecule here, right, so the depth 90, which shows the CH, right, so that means that this signal here and this signal here, those are both CHs. Okay, these signals down here, right, this is the negative, right, so this is the 135, so the ones that are negative here, those are the CH2s, right? Okay, we already know that these are CH right here. Okay, so that means these guys here, which don't appear up here, those have to be CH3s. Okay, so like that. So that's how you figure this out. And then there's also a signal here, see, about 132, so like that. So that doesn't appear in any of these guys. It doesn't appear there, or it doesn't appear there. Okay, you can maybe kind of see it there, but basically not. Okay, that means that that's the quaternary carbon, right? So like that. So the which should actually be right there. Okay, and so that's how this works. Okay, so right, so there's CH3 sort of in the middle, or CH2 in the middle there. CH2, CH3, CH3, CH3. Right, these CH2 is here, right? Because those were negative. These two showed up in the depth 90. This one didn't show up in any of them. Okay, so that's how we know. And if we put these guys together and combine it with the chemical shift data, we can go with this, right? So okay, okay. So we're gonna do it. We're gonna do a homework problem. So like that. So okay. So like that. So we're gonna put that. Okay. So here's the problem. 13.63. Okay, so we have a structure. Okay, compound E. We're going to need a chemical shift term. That. Okay, so we'll bring that up when we need it. Okay. Okay, so here's the compound C7H12O2. Okay, so you have the C13 data. Okay, that's all we've got. Okay, so the decoupled one, right? Notice how there's 1, 2, 3, 4, 5, 6 signals. Okay, but we have 7 carbons. Okay, that means that 2 of them are going to be equivalent to each other. Okay, so we need to keep that into account. Okay, there's going to be 2 that are equivalent. Okay, so with that, so if you remember, right? So depth 90 does what? That does CH, right? So that's CH, right? So we know that this guy, the 28, that's CH, right? And the 129.8, this guy here, that's also a CH. Okay. Now that means, okay, and so the positive, okay, so that those we know, right? Okay, so the positive peaks, right? So 135, right? So this is CH, CH2, CH3, right? That's what 135 will do. Okay, positive peaks, right? That's CH and CH3, and the negative peaks are CH2, right? So we know the 70.5, that's a CH2. Along with the 129.0, right? So CH2. Okay. So that means what? Well, what does that mean? CH2, right? And then this guy here is also a CH2. Okay. Okay, so now this one here, right? We already know that these guys here, those are CHs, right? Because they also appear up here, right? So that means this 19.1, that's a CH3. Okay, because it only appears here. If there's a CH, it would appear in both, right? So, but not, right? So this guy here is a CH3. Okay, and we're missing one, right? We're missing this one here, right? So what does that mean, right? It doesn't appear in either one of those, so this must just be a regular C. Okay, so here we go. Now we can come back to here and we say, okay, so how many, right? So we have 1, 2, 3, 4, 5, 6, right? So we're missing a carbon, so we have to deal with that, right? So we have 1 carbon that's equivalent, right? But let's look at the hydrogens, right? So, we have 3, 6, 7, 8, 9, 10, excuse me, 3, 4, I don't know, sorry about my counting, 3, 4, 5, 6, 7, 8, 9. So what are we missing, right? We're missing a CH3, the equivalent of a CH3. We're missing a carbon, right? And we're missing 3 hydrogens, right? So the easiest thing that we're missing, right, is a CH3, which probably means this guy here is times 2. This is probably going to be the equivalent one, right? So if we're missing a CH2, right, that means that one of these guys would probably, one of these 2 guys would be the equivalent ones, right? If we were missing a C, right, just a C, we had all the other hydrogens accounted for, right? Then this would be the equivalent one. If we were missing 1 hydrogen and 1 carbon, it would probably be this one that's the equivalent one. But here we're missing a CH3, so it's probably going to be this one here. Again, you got to figure, you got to work on this. You should, sort of go through each time. Okay. Now, okay, so we have the pieces, right? We probably have 2 of these CH3s, right? We have a CH, CH2, CH2, CH, and then a carbon of something. That's okay. So next we're going to look at the chemical shift, see what that tells us. Okay. Okay. So these guys here, the 19 and the 28. Okay. Those are right in here. Okay. We don't have any halides, right? So it's not like we have to deal with that. So these things here are probably connected to just carbons, nothing electronegative. Okay. Now this guy here at 70 is probably connected. This guy here is probably a CH2 connected to an O, right? Because it comes right smack dab in the middle of where the CHs usually show, or the COs usually show up. Okay. This guy here and these 129s, right? That's going to be right down in here, right where these guys show up. Okay, so, right, so we have a CH2, CH. But where's the only time we can have a CH2, right? This guy here can have a bond on it. This one, all 4 of the carbon bonds are done, right? So that means this guy here, this group, is at the end, right? There's no other way that you could have a CH2 attached to a double bond, right? We figured it out, right? CH2, CH, right? CH2 on a double bond. The only way to do is if this group is at the end of the molecule, it's at one end, okay? So we figured that out, okay? And then the other end has to be CH3, right? That's the only, well, I guess it could be methyls, stuff like that, so, okay? But probably at the end, so, okay? And then where is this, okay? So we probably know that part. Right, and then this part here, 165, well, that falls right smack dab into a C double bond O, right? It's not going to be an aldehyde, right? Because if it's an aldehyde, right, you would have an H there, right, being the CH, right? But it's probably a ketone or an ester or something like that. Okay, something like that. So either carbons on either side or carbon and oxygen, something like that. Probably not 2 oxygens, right? Because we don't have two to deal with, right? Stuff like that. So we either have carbons on both sides or a carbon and oxygen on both sides, or carbon on one side and oxygen on the other. Okay. So now we have to come in. So we sort of know what the chemical shifts are looking at, what that's telling us. Okay. So now we need to know the parts. Okay. So now this comes in. We have all the information we need. We just need to start fiddling around with it. Okay. So we know that the CH2 is going to be at one end, right? Okay, we know we have a C double bond O, okay, with something hanging off, not hydrogens, right? So that's not the other end. Okay, we have a CH2 O, okay, and we have a CH. We have a CH, and we have 2 CH3s. Okay. Now, let's say we did a CH O CH2. Okay, let's say we did that. Now, what would happen to these chemical shifts, right? This would be normal, right? So this would be at 70, right? It's in red so you can see it. This would be at 70 like normal, right? Because it would be there. But what would happen with this one? This would also be at 70, right? That's not what we get. Okay, so we can't have the connection like this. Okay? Because that would move this chemical shift too. This would be closer up to there. Right? Stuff like that. So like that. So okay, so like that. So it can't be connected like this. Okay, but it could be, say, connected like this. Like this, right? Now the other option would be, right, so this would be normal, right? It's just right to another carbon, right? An oxygen, right? Another thing you could do is say, well, what if it's CH2O, let's say it's one of those CH3s. Well, we can't do that, right? Because this carbon, right, we need another CH3 hanging off of there to make these two equivalent, right, as they're spinning around. Okay? So it can't be that, can't be that. But this might be a way to put them together. Okay? Okay, so like this. So we may have something like this. Okay? Now this, right? So like that. So this isn't connected to that, right? So like that. So we know we have this. We know we have that, right? So what about CH2O, CH2, something like this. Okay. Well, that would give the chemical shift here, right? That would be fine. That's 70. But this one here is right where we need it to be, right in the alkyne. So like that, so alkene, excuse me, for an alkene. If you had an extra electronegative atom on it, it would shift even further downfield. And so this one would probably be, say, 150, right? And this would be 129, something like that. It would shift it way downfield. So that doesn't really make sense to what we're seeing here. They're both going to be attached to just basically carbons, okay? So that's probably not likely. So like that. So, but what we could do, okay, we could say, hey, let's make an ester out of this, right? And then connect that on one side, like that. Okay. And then, okay, so 1, 2, 3, 4, 5, right? We still have 7 carbons, right? But they're both missing the CH3, so we put a CH3 here, a CH3 there. That's the only place available, right? Because this has 4 bonds, this has 4 bonds, this has 4 bonds, that has 4 bonds. This is the only place available. And oh hey, they are equivalent to each other, right? As they spin around that bond there, right? As they spin around, these two guys are going to be equivalent to each other. So here's the structure. Okay, like I said, it's a lot of puzzle solving, right? You sort of have to go back and forth. How do these little puzzle pieces go together to all make sense? To not only the CH3, you know, how many hydrogens there are on there, but also do they make sense on the chemical shift data that we're seeing? Okay, so like, you know, here, right, it doesn't make sense that it would be CHO, CH2, right, because this would be shifted downfield, and so would this one, but that's not what we're seeing. Okay, they would both be about 70 if that was the case, but that's not what we're saying. You know, one is just connected to regular carbons. So there we go. So like that. So again, it's something you need to practice. I wish there was a better explanation for that, but that's the biggie. Okay, so how do you use carbon NMR, right? So again, you're going to see structural information, right? Stuff like that. So yeah, that's going to help. Let's see. A little bit of glare on that. So let's see if that helps. Okay. Well, I guess it did. Anyway, so if you have this, okay. I don't know why it's going so bright. Kind of hard to see. Sorry. I don't know why we're getting such glare on this. But what we're seeing is let me turn. There we go. I wonder if that's good. Is that easier to see? Maybe that'll be a little bit easier to see for you. Okay, so when you have these two molecules here, right? So if you have, right? So we run a reaction, right? We could get two products, right? So we get CH2 like that, CH3 like that. Okay. And so there's two possible combinations for these things, right? So two different ways. As you can look at the signal. And actually, in some ways, all you have to do is count the signals, okay? Because if you notice, if you get this structure here, right, there's a nice plane of symmetry here, right? So really, you'd only get 1, 2, 3, 4, 5 signals, right? Because these two would be equivalent, these two would be equivalent, right, to each other. But for here, there's not really any plane of symmetry, so every carbon is different, right? So you have 1, 2, 3, 4, 5, 6, 7. 7. You have 7 signals for this one. And if you count it up, it's really hard to see in here, but it's 1, 2, 3, 4, 5, 6, 7. Okay, so because you have 7 signals, 7 distinct carbon atoms, right, it's going to be that one there. So, okay, so like that. So for hydrogen NMR, you're going to get the similar sort of equivalence issue for as you see with carbons. Okay, so how do you tell if two protons are equivalent to 2 hydrogens there? You can substitute a hydrogen at that some sort of X, right? Fluorine, I don't know, and see how it changes the molecule. If it does it change the name of the molecule, then it would, right? So like that. So, or does it create enantiomers or diastereomers, right? Then we're going to know, right? So we're going to say, okay, here, if we're going to replace these hydrogens here with it, right? So like that. So if we replace it here, right? So these 3 here at the methyl group, right? So let's say we put a fluorine here, right? If we name those, right? Those would become. It would always be 1-fluorobutane, right? If we put it here, 1-fluorobutane. Put it here, 1-fluorobutane, right? So these guys here and these methyl groups here, those are all equivalent hydrogens. Okay. Now, if you put it on one of these internal ones here, it just so happens that it would be 2-fluoro. If we said substituted the hydrogen with a fluorine, right? It'd be 2-fluorobutane, but right. So they would be constitutional isomers, right? Sorry about this. But the molecule itself would be different, right? So if they're non-equivalent, right, so we can have issues, right? So we put it here, right, versus these 2 guys here, right? Those would be there. But if we put a fluorine here versus fluorine here, what does the pair of these 2 molecules look like? This would be 1-fluorobutane. This would be 2-fluorobutane, right? So they're constitutional isomers to each other, so they're non-equivalent. Okay. If you compare this hydrogen with this hydrogen or this hydrogen with one of those over there, the molecule stays exactly the same, right? 1-fluorobutane. If it was over here, if we substitute over here, it'd be 1-fluorobutane. So these are actually equivalent to each other. These hydrogens here on this CH3 and on those CH3, those are what are called homologous, because the names of the molecules will be the same. Okay. Now you do have to be careful. If you create a new chiral center, right, then it could be an issue, right? So like that. So if you create, if the protons are pro-R, pro-S, right, so I don't know why it chose this one. So I think this might be the wrong picture, right? But if you have a chiral center, if you create a new chiral center, okay, so like that, so actually it would be, so let's say this one here, that was a mistake in the picture, right? You would actually, if you compare these 2, that X and that H right there, right, you would create an S version or an R version of the molecule, right? So now you've created a new chiral center, the first chiral center on there. When you do that, you say that those 2 hydrogens are enantiotopic, right? Because if you substituted in fluorine, the molecule now becomes has a new chiral center. It means it has 4 things on there. It's the first one you put in there. Now you could create enantiomers depending on which one you put in there. If it already had a chiral center in it, there's a good chance that, and then you put in there and created a new chiral center. Okay, now those are called diastereomers, right? So these 2 guys are diastereotopic. Okay, so about that. So okay, so about that. So okay, so how are we gonna do this? Okay, so here we go. Okay. Okay, so these two hydrogens here. Okay, so let's say we put an put a fluorine in one of these positions. Okay, well now we've created a chiral center, right? Because of FH and then right, this is CH3, right? It's C double bond O. There's now 4 different things at this chiral center. That's the only one that's created, right? So that means since we've created a chiral center, By substituting with fluorine, that means those are enantiotopic. Okay? Right, there's a chiral center now formed there. Since we're creating its first chiral center, that means that it's enantiotopic. Okay? So if we do this one, right? Okay, so let's say we're going to put a fluorine there. Okay, so we're interested in that carbon there, right? So now, right, we have an F and an H, right? So CH2, CH2, right here, okay, and then you go out. Those are the same, right? So CH2, CH2. Right? Now you go out and now you have a CH2. Now you have a CH because it's got that hydrogen, right? So now you've created a chiral center. Aha! But you've also created a chiral center there too, right? So if you go backwards, right, so you have a CH, right? Oxygen H, CH2, CH2, right? CH2, now it's a CH with a fluorine on it, right? So actually now you've created two chiral centers. So this is actually, so this guy here is actually diastereotopic. Okay, because now you have two chiral centers in the molecule. When you swap out a hydrogen and you just make one chiral center, and the molecule now has only one chiral center, it's considered enantiotopic. When you put in the fluorine, now you take a look at the molecule, now it has two chiral centers or more. That means that these two original hydrogens were diastereotopic. Okay? I know it's a little confusing. So, right? Right? Okay. So let's say we're going to put a fluorine there. Okay, so fluorine. There's a fluorine hydrogen, sorry, CH2, CH3, right? Okay, oh, that you make a chiral center there, right? Ah, but there's also, notice there's an H here. There's a chiral center here, okay, because CH3, C double bond O, bromine, right? So now there's two chiral centers in the molecule, right? Where there was originally one. There was originally one chiral center, now we have two, since it's diastereotopic. Okay. So put a fluorine there, right? So if we're, right, so we don't make a chiral center, okay, because there's still two hydrogens on there. But this compound would be 1, 2, 3, 4, 5, right? So it'd be 1 fluoropentane, right? If we took the analogous, if we took one of the other ones, say we took the one down here, right, and said, okay, instead we're gonna put fluorine here, right? What's the name of the compound, right? It's still 1 fluoropentane, right? So that means that these guys are homologous. Okay. Okay. So, okay, again, I'm going to take one of those, put a fluorine there. Right, so now we have a CH2, right, CH2, right? Hydrogen, right, so fluorine, hydrogen, right? There's no other chiral centers in there, right? CH2, CH2, and then we have CH2, CH3, right? So that means that this side and this side are different, right? This is an ethyl, this is a propyl, right? So now you make just one chiral center. Right, so now that would be considered an antiotopic. Ah, antiotopic. That means these hydrogens are an antiotopic because when you substitute a fluorine, you've now created the molecule now has one chiral center. So, okay. Now this one here, we compare these two, right? So. Right, so let's say we put a fluorine here, the molecule becomes 1, 2, 3, 4, 5, 1 fluoropentane. Right? Instead, we put the fluorine, say here, right? 1, 2, 3. This would be 3 fluoropentane. Right? 1, 2, 3, 4, 5, right? These names are different, right? So they're non-homologous. Okay. Again, do some practice. It's not a huge deal, but do this would be right. Intertopic, distereotopic, homologous, right? Antiotopic, unrelated, right? There we go. Okay, back to the regular NMR, right? So this is just showing you how the hydrogens could be related. Okay. Okay, back to the chemical shifts. You're going to have very similar chemical shifts to the NMR or to the carbon NMR, right? So if you just have regular carbons, right, they're going to be sort of in this range. If they're one away from a double bond, or they have electronegative atoms hanging off them, they're going to be sort of in this range here. If it's hanging directly off of a double bond, it's here. If it's hanging off a benzene, it'll be here. And if it's part of an aldehyde peak, and I wish they showed this, is the only thing that's way out here. An aldehyde peak is down here at 10, 9.5 to 10. It's the only thing that shows up here. Okay. Okay. So here is the list. Okay. And again, I'm not going to make you memorize this list. I'm not going to make you memorize that carbon 13 shift either. Shifts here. I'll give you this list. You just need to know how to use it. Okay. Stuff like that. So why? Why don't I make memorize? Because people don't memorize these things, right? So if you memorize them, it's because you're an organic chemist. You need to use them all the time. If you don't, and presumably you aren't going to be, you have this you either just Google it or you have it taped by your desk, stuff like that, so you can look it up, right? There's no reason that you sort of need to sort of generally know sort of like what these guys are, right? But you need to figure out. So for the MCAT, okay, so for user taking pretty much anything in here, this is how you know. General rules. Just carbons. Okay, nothing funny hanging off them. Sort of around in here, you're either one away from a double bond or you're one away from something that has electronegative, oxygen, nitrogen, things like that. That's sort of in this range. Right, so I should say in this range here. Okay, sort of the 2 to 4. That's where this is. Regular carbons, I don't know, 0 to 1.5. Right? Electronegative or one away from allylic is here. 5 to 6, vinylic. It's hanging right off a double bond. Aromatic, sort of 6.5 to 8, right in here. Aldehyde here, right? So there you go. That's all you sort of need to know. You can kind of figure it out from there, but you don't have to memorize this chart if you sort of know this general trend. Okay. Stuff like that. So there you go. Okay, so chemical shifts, right? So we're gonna figure this out, right? So look at the chemical shifts, right? So should have this printed out. Sorry. Okay, so what you need to sort of do is see what's hanging off of it, right? So this is, right, so we're going to start at this end and we're going to work our way here, right? So this guy here, the CH3, right? You look at your chart, right? See if I have a bigger chart. Oh, here it is, okay? Hopefully you can sort of see this. Okay, so chemical chart, right? So you look at here, look in ether, somewhere between, right, it says 3.3 to 4.5. Somewhere around in there, okay? These guys here, right, so these two are going to be equivalent, and these two are going to be equivalent, okay? So, but they're all going to be part of the aromatic part here, okay? And so benzenes always come up between about 6.5 to 8, okay? This guy here is hanging directly off of a double bond, right? So vinylic, right? Those always come between about 4.5 and 6.5, right? So that one and this one, 5 and 6.5, right? This guy's here, right? This carbon here is one away from a double bond, okay? So that's, excuse me, so these are alkene, right? So this is, no, excuse me, those are vinylic. The, this is allylic, sorry, confusing. something like that. So this usually shows up between 1.6 and 2.2. Okay. And then this last one, right? So this one is just a regular CH3, right? So it's going to be 0.7 and 1.3. Okay, so that's sort of how you know. And again, these are sort of ballpark numbers, right? Right? So like that. So, but that's about what we're saying this, right? So like that. So these are sort of what a simulation would look like. Okay, so they all sort of fall into this range. I'm not going to make you necessarily do this, right? Stuff like that, but you're going to need to know that for solving the problems. Okay. Okay. Where would we expect molecules that are not equivalent? Okay. So with that, so here we go, and it would the spectrum would look something like this, right? So 0.9, right where we would expect them to go. Okay, they'd be right in these ranges here. Okay. So there we go. Now the other thing that we can know about these, okay, is if you were to calculate the area underneath these peaks, okay, integrate them like in calculus or whatever, something like that, so you can learn a lot of information about that. It turns out that these guys here, these have two equivalent, right? So for this CH3, right, which would be, let's see, it's this one here. Okay, if you calculate the area under the peak, it's 3 times as much as, say, these guys here, the H's that are here, right? There's 3 times as much. Okay, and so you'll sometimes see this as a sort of a area under the peak, right? So you can sort of see from the ratios, you can see how many hydrogens are hanging off of it, are associated with that peak, right? So this is 3 carbons, or 3 hydrogens, 2 hydrogens, 3 hydrogens, 1, 1, 2, 2. Okay, no, and again, it's one of those, these two are equivalent, these two are equivalent, right? So they integrate to 2. Okay, stuff like that. So this is going to integrate to 3, this is going to integrate to 2, integrate to 1, 1, 2, 2, 3. Okay, and that's what we see here. Okay, so what are they, right? So these guys here, right, these are all equivalent. The CH3s, right, because they're spinning around, right? So that's actually going to be equivalent to 9 hydrogens. That carbon there, right, so that would not have any, right? These two guys are equivalent, right, because, again, these two carbons, right, are 1 away from this T-butyl group and 2 away from this methyl. So these two are equivalent. These two are equivalent too, right, because they're 1 away from this methyl and 2 away from this T-butyl group. So these signals here would integrate to 2. This would integrate to 2. And then this one here would integrate to 3, right, because there's 3 hydrogens hanging off of that carbon. Okay. So, like that. So it'd be these. You would get a 9 hydrogen signal, right? A 2 hydrogen signal, a 2 hydrogen signal, a 3 hydrogen signal. Okay, this carbon here wouldn't show up, nor this one, right? Because there's no hydrogens off of them. So we would only see those in the carbon NMR, but not the hydrogen, because there's no hydrogens taking off of them. Okay, and so for this one here, you would say, oh, hey, it's a 3 carbon signal, a 2 carbon signal, or 2 hydrogen signal, and then a 3 hydrogen signal. But if you take the molecule and just flip it like this, right? These guys here are actually equivalent to each other, right? Because you just flip the molecule, right? It's slow, right? So you have to flip the molecule, right? So what you would actually end up getting is a 6 carbon signal and a 6 hydrogen signal and a 2 hydrogen signal. Or more specifically, you would actually get a 1 to 3, right? Or a 1, in this case, a 1 to 1 to 1.5 to 4.5, right? Which you would then double, right? Those are the ratios. But I'm going to give it to you already, most of the time, 99 times out of 100, I'm going to give it to you as the regular, already proper integration, stuff like that. So, but do realize that it does sometimes pop up. Okay. So there you go. Now, spin splitting. Okay, so the magnetic field of the individual protons, right, can interact with the magnetic fields of its neighbors. Okay, and what's happening is what we call spin coupling or spin splitting of the signals. Okay, so the individual protons can be either aligned or opposed to each other. Okay, so they're either going to be like this or they're going to be like that. Okay, so so they're either going to be together or they're going to be apart. Okay, and so you sort of look at, and that causes them to break. Okay, depending on if you have a bunch of them like this or a bunch like that or whatever. Okay, and so what happens is the neighbors. Okay, so notice how these are broken apart. Okay, this signal is not a single signal; it's actually 4 little peaks put together. This is 3 little peaks put together. Okay, and this is considered one signal. Okay, and it turns out that it's the neighbors that are going to be splitting. What's going on with that? Okay, and you get this sort of, what do you see? Okay, so we have these hydrogens, right? These hydrogens here, right? So the combination of, right? So this CH2 with the 3 next to it, right? You could have, you could have all one way. You could have one of them going one way and the other 2 going the other, or the opposite, or all going that way. These are the 4 combinations you can have with this signal and next to these 3 other signals. These are all 1, but you have 2 over here, and so these are the possible combinations of them. Okay, but the net effect is what's called the n+1 rule. Okay, and so the n is the equivalent number of protons on the neighboring carbon. Okay, and so if you have, right, these hydrogens, right, so if their neighbor has, right, so the neighbor is this, right, CH3, right, so that means the neighbor has, you get 4 signals out, so that means n+1, right, so the neighbor is going to have 3 carbons on it, or 3 hydrogens on it, right. This one here is going to split into 3 signals, right, okay, so that n+1 is equal to 3, right, that means the neighbor, it's neighbor plus 1, okay, and so the neighbor's going to have 2, okay, right, so it's always n+1, right, okay, so if you have, n+1 equals 4, right, that means the neighbor has to have 3, right, so it's a CH3 group, right, if the n+1 is equal to 3, right, that means the neighbor has 2, right, so it's a CH2 group, okay, so like that, so the n+1 rule, right, so what we're going to say is if there's no, right, so if we have 1 signal, right, it's called a singlet, 2 signals, two signals, it's split into 2, it's a doublet, 3, it's split into 3, it's a triplet, into 4, it's a quartet, 3 is, 4 signals is a quartet, 5 signals is a quintet, a septet, things like that, okay, and so what's happening is, right, so here is a septet, right? So n+1 is equal to 7, which means the neighboring has to have 6, right? It's a quintet, which is 5, right? So with that, so the neighbor, right, n+1, that means the neighbor has 4. The quartet, which is 4, right? So with that, so we have 4 signals, so the neighbor plus 1 is 4, so the neighbor has to have 3. That's all we're saying, okay? Okay, and you can also look at this, and we're not going to emphasize this, but just be aware of it. You can get the distance between these peaks here. Okay, that's what's called the coupling constant. And so if you have two signals where the split between those peaks is the same in hertz, that means that those 2 things are interacting with each other. They most likely are going to be interacting with each other. Okay, and so like this set of peaks, the splitting constant, like these 2 peaks, this coupling constant, which means the distance between those peaks, let's say 9. Okay, that means these 2 guys are interacting with each other. If these 2 sets of peaks over here, the distance between the peaks is 7 hertz. Okay, that means that these 2 are probably interacting with each other. Okay, you can sort of see, it sort of helps to provide information on who's connected to what. Okay, something like that. So you don't necessarily, you're not going to get it very often, but it's something to be aware of. Okay. Okay. So how do we know this? Okay. So with that, so splitting. How do you know? Okay. So equivalent protons do not split each other. Okay. You're just looking at neighbors. Okay. So with that, so okay. So with that, so okay. The n+1, and don't forget the n+1 rule. The protons have to be on adjacent carbons, right? So these 2 guys split. Okay. Right, so this is the neighbor, the direct neighbor. You can get further away, but that's way more complicated than this course. Okay, but these 2 guys, these blue ones, too far away. Right, there's a carbon in between them, so they do not split each other. Okay. So you have to be a direct neighbor. Okay. And then multiplets with the same coupling constant are probably interacting with each other. They have the same J. They have the same coupling constants. Okay, so what happens when you have more complex ones? So what'll happen is like you'll get things that are aligned on top of each other, and it just looks like a big mess. Okay, so all of these hydrogens, right? They're all on this benzene. They're all kind of like on top of each other. Lots of times we'll just call that a multiplet. Okay, stuff like that. So and there's nothing you can do. Stuff like that. So I'm going to try to avoid those sorts of things. Okay, or tell you what's going on. Okay, but benzene is where usually they all kind of squish together, and it's really difficult to figure it out. Okay. Now, what happens if you have neighbors on both sides? Okay, you're going to get splitting from one. One's going to split first, and the other's going to split those splits into more splits. Okay, and so what can happen is, okay, so let's say you've got something like this. Okay, so you have a benzene, right? I'm going to draw it like this so it's a little bit easier to see. Okay. Okay, so so this one here, okay, that one, right, it's going to integrate, right, one hydrogen, right, because that's how many. So the integration is going to tell you how many hydrogens are on that carbon, how many equivalent hydrogens are on that carbon, right. So this is going to integrate to one, right. That's going to integrate one hydrogen, right. This is going to integrate one hydrogen. Okay. Now, what's the splitting going to look like? Okay, so this one here, the splitting, right? That's a carbon on this side, no hydrogens on it, right? So we're good on that side. This side here, you have this carbon here. This one carbon neighbor has just one hydrogen, right? So 1 plus 1, right, equal to 2. Right, so this is going to be a doublet. So this is going to be a one hydrogen doublet. This signal here, right, again, it's going to be one hydrogen integrate, right? It doesn't have any neighbors on this side, right? It just has the oxygen, which no hydrogen. But this side, right, there's one hydrogen on this side, right? So you're talking about 1 plus 1, right? Neighbors plus 1 equal to 2, so that means it's going to be a doublet as well. Okay. Now, this one here, you have it interacting between these, right? So that's going to make it into 1 plus 1, right? You have a neighbor on this side, right? So 1 plus 1, so that equals 2, so it's a doublet. Okay, but you also have this neighbor here, right? This neighbor on that side. So again, this is going to, what happens is it takes that doublet, right, and it splits it into a 1 plus 1, another doublet. Okay, so a doublet. And so what happens is you actually get a doublet of doublets. Okay, so it takes those initial two and it splits those into further doublets. Okay, and so it actually splits it up. So what you're going to see is 4 peaks for this one hydrogen. And you're going to say, oh, it's a CH3 next to it. No. Okay. You have to be careful, right? And if this was a CH2 over here, right, you would have a doublet from this side split into triplets. Or you can have a triplet split into doublets. Sometimes if this was a CH3 on this side, you would have this split into a doublet, and then it takes those doublets and splits it into a quartet, right? So it's a quartet of doublets or something like that. It gets really, really crazy. Okay, but if you know if you see something of something, that means you have things on both sides. Okay, if you just say doublet, that means you only have something on one side. But if you have something of something, like doublet of doublets or triplets of doublets or quartets of triplets or something like that, it gets really complicated, right? That means you have things on both sides. Okay, you have neighbors on both sides. Okay, okay, so if you notice, the splitting pattern for this one is different. Okay, the more you don't have this real you don't have this sort of Gaussian sort of thing, right? It just sorts of it just sorts of it can go flat. Now you can actually get a little bit of angle, and sometimes they angle towards where they're splitting with. Okay, stuff like that. So if you look at a quartet, the height says 1 to 3 to 3 to 1, but for a doublet to doublet, it says basically 1 to 1 to 1 to 1, roughly. It get a little more complicated than that, but roughly it's going to be all equivalent to each other. It's going to be flat. Okay, but this one is going to be 1 to 3 to 3 to 1. That's the ratio, and here it's 1 to 1 to 1 to 1. Okay, so it's not quite as easy to see on this one here. But I will tell you if it's a quartet or a doublet doublets. Okay, I'm going to tell you that in the on the exams and stuff like that. So you don't have to worry about that. Okay. Okay, so again, how do we figure this out, right? If we do this experiment, right? So if you look at this versus this, okay, this one here is going to have, it's all going to be CH2s all around here, right? All around here, all around here. That's not going to change much, but this is a CH. You're going to have the CH molecule here, right? You can have a CH integration. And this one is going to be another CH2. Okay, but this one here, you're not going to have any you're not going to have any CH integration. So you're not going to have anything integrate to one. But you're going to have a big CH3 integration, which isn't here. Right? So if you just kind of look at what you're seeing, just the integrations, you don't have to even solve the molecule. You'll be able to know which one it is. Okay? Because this one's going to have a CH3 integration, but not a CH. This is going to have a CH, but not a CH3 integration. So that's a good way to looking at this. Okay, stuff like that. So okay, so this one here, right? This one is going to have the big CH3 right there. Okay, this one doesn't. Okay, it has a CH2. Okay, so you can look at chemical shifts, stuff like that. So okay, so how do we solve these problems? Okay, I was trying to figure out a way to sort of standardize a way of thinking about these. It's a little more complicated than that, but it's not horrible. Way of doing this. Okay, so when you get a formula for this thing, okay, one of the first things to do, right, is to just go ahead and do the DOU. It gives you some information on what the molecule might look like. Okay, so just run the DOU. It's really easy to do. It takes 5 seconds. You do it. You get an idea for what you're looking for. Okay, it's not a bad idea to just look at the formula itself, right? To say, are there oxygens? Are there nitrogens? Are there halides? Are there, what's in there? Okay, and that DOU sort of gets you in that mindset. Okay, so what you're looking at. Okay, so then the question comes, okay, if I have 5 carbons on this thing and I have 5 peaks, okay, you can just count the number of types of signals that come out of there. That means that they're all that they're every carbon is unique. Okay, if I don't, right, if I have a 5 carbon sample, but I only have 4 signals out, that means 2 of them are going to be equivalent to each other. There's probably going to be some sort of symmetry to it. Okay, or you have to be careful. Or there's like a C double bond O, or there's going to be something that doesn't have any hydrogens on it. You have to be really careful. There could be some symmetry to it. There could be there could be something that doesn't have any hydrogens on it. Okay, so as you're sort of building up the information from the sort of the peak integrations, right? It's going to tell you that what's going on here. Okay, can we account for all the hydrogens? Can we not account for the hydrogens? Can we account for all the carbons? Can we not account for all the carbons? Okay, so about that. So what do the integrations look like? The next thing is, what do the chemical shifts tell you? Okay, there's a lot of fingerprint regions like the aromatic, aliphatic, right? So the aliphatic is going way down near 0. Okay, the C double bond C. So what's coming off of if you directly off of a double bond, that's really common, right? That's the only thing that occurs there. And things like the aldehyde peak, that's the only thing that comes down at 10. Right? So there's these fingerprint regions where it can help you along. Okay, and then we're going to start. What do the splitting patterns let you know about? What do the integrations let you know about? What do the splitting patterns know about? Right, and if they're coupling constants, that means they're probably right next to each other. Okay. Okay, so here we go. So the first thing you do, right? So this is going to be the type of question that you get, right? I give you a formula and I give you signals, right? So about that, I give you signals. You get, right? So we get, so about that. So we have 3 signals, 3 carbons. Probably going to be all equivalent to it. We'll see. Okay. So first thing we do, right? We run a DOU. Okay. Okay. So right? So there's 3 carbons, right? There's no nitrogens, but there's a halide, right? And there's 5 hydrogens. So you come out there's 1, okay? So that means we either have a ring or a double bond, okay? So like this. So we have to keep that into account, okay? Now, what does this? Okay, so we know that, right? So now, what does the chemical shift? What does the chemical shift data tell you? Okay, so you look in the region, right? So you look in this. Right, so you look here and you say, okay, where does this tell you? Okay, so vinylic or allylic, so it's 1 away, right? So 1.6 to right, so for this. So it could be, it's darn close to that. Okay, so if it's a 1/10 away, 2/10 away, there's a good chance it could be there, right? So like that. So we have to keep that in mind. Alkynyl, right? So that would be 2.5 to 3, so that would be close to this, okay? But it can't be alkynyl. Why? It's because we only have, alkynes have 2 degrees of unsaturation. We only have 1, okay? So it can't be an alkyne, so we can actually get rid of that one, okay? Now the other thing is, right, so you get these signals with 5, right, that the only thing that shows up is actually, right, in this region is the vinyl. So these 2 guys are actually going to be right apart from each other. Okay, so like this. So these guys here are both going to be part of a C double bond, C. Okay, so this is probably going to be hanging off of the C double bond, especially since there's 3, right? So this says that there's going to be a double bond, right? Because it's the only thing that shows up, and then this is going to be 1 away. Okay, so like that. So next up. Okay, so we know it's a double. These two are on double bonds. This is 1 away from a double bond. Okay, so what does the splitting pattern tell you? Okay, and so this is kind of how I like to write it. So you have 2.3 sigma 3H singlet, 5.35 sigma 1H singlet, 5.54 1H singlet. Okay, so here, so this says, okay, so this is a CH3, right? CH3, okay. Now, what's next to it? Okay, so that tells you, right, so this is the integration, right? Integration, right? This is the split. This tells you how many are on your carbon, right, in theory. This is how many neighbors it's got, right? So it doesn't have any neighbors, right? It's C. Okay, so this guy here, right? This is a CH, right? That's what that's telling you. How many neighbors does it have? Well, the split is, right, because this is, right, n+1, right? It's the same. So if we get 1 out here, right, that means it's, the only way we can get 1 from this equation is n equals 0, right? So again, n equals to 1, right? That means that n is 0. Because n+1 would equal 1, so it means n is equal to 0. Same thing down here, right? CH, C. Okay. Now we do have this bromine we have to take into account. Okay. So it's going to be something like this, right? The other thing it does, right? So if this is part of a, right? So if this is part of a C double bond C, right? That does take into account our right? So our degree of unsaturation. So right. So let's put it there, right? We're not going to have a ring, right? Because we can have a ring and a double bond. That means 2. We have just a double bond. So it's going to look like this. Okay, so now where does this come? Okay, so we know we have a CH3, right? So the only place we can put it is here. It's the only place we can put it. Plus that makes sense because of the of this here, right? So that it's 1 away from the double bond. Okay, and so here we go. So right, so we need 1 bond here, right? So we could have an H here and an H there. Okay. But, okay, so this carbon has its 4. This carbon, right, 1, 2, 3, 4, that has its 4, right? This one, carbon is 1, 2, 3, right? So that means that the bromine would have to go here. Okay. Now, the other option, okay, so, but does it make sense? Okay, we have, if we had this molecule, now the important thing is to go back and does this make sense? Okay, so this would be what? So this would be a 3 hydrogen, not this, right? But if you look at here, right, How many neighbors does it have? It has 1, right? So 1 plus 1, right? So it has 1 plus 1, right? So it would be 2, right? So this would be a doublet. That's not what we're seeing. We see a singlet here, right? Same thing with this one, right? So it would be what? It would be a 1 hydrogen. Well, that makes sense, okay? Okay. Well, but again, it has a neighbor, right? So 1 plus 1, 2, right? So it would be a doublet. Okay, so it would be a 1 hydrogen doublet. That's not, and then this right here, right? We have 1 on this side, so that would be a doublet. And then we have 3 on this side, so that would be a quartet. So we'd have a doublet or quartet. That's not what we see. Okay, so even though this sort of makes sense, right? This is how you would think about it. It doesn't make sense as far as the splitting patterns go. Okay, and so here's another way that you could put it, and this, I made this intentionally hard to sort of show you. Okay, what if we put it like this? And actually, here, let me actually write the CH3 down here. Okay. So it helps to illustrate what's going on here. Okay, this carbon here, right, has its 1, 2, 3, 4 bonds, right? This CH3 has its 1, right? And then this guy here has the bromine. It's missing one, so the bromine would go here. Okay, notice how, remember how double bonds can't rotate? Okay, and so you're going to say, oh my goodness, this one should be a 2 hydrogen one, but I pulled a fast one on you. These things are actually not equivalent to each other, right? So, right? And so, right, because this one is only seeing this bromine, and this one's only seeing that methyl group. Okay, and so this one is going to be seeing a totally different environment from this one, so they're not equivalent. So they're going to give different peaks. Okay, and so here we go. So again, does the splitting pattern make sense? Okay, so for this one here, right, it's a CH3, right? So that would be a, so integrate to 3. Okay, what about the neighbor? Right? The neighbor doesn't have any hydrogens on it, right? It just has the bromine, right? And so, right, n plus 1 equals 1, so that means that it's 0 plus 1 equals 1, right? So that means it's a singlet, right? So there's no, that means that if we're seeing a singlet, it can't have any hydrogens on it. Okay, what about this one, right? Again, 1 hydrogen, right? This isn't a neighbor, right? It's on that hydrogen. This is the neighbor. Any hydrogens on there? Nope. So it's a singlet. What about this one? Well, it integrates to 1 hydrogen because we're dealing with 1 hydrogen, right? But again, that's not a neighbor, right? This is the neighbor here. It doesn't have any hydrogens either, right? So we're going to get a singlet. So this is the only way you can do it to make sense of the data. Okay, this is the 2 possible ways you can do it, but this doesn't make sense with the data. This is the only thing that makes sense with the data. Okay, and the reason why is because you don't get rotation around this double bond, and so this hydrogen, right, is feeling the bromine. This thing could care less about that bromine right there. All it's seeing is this methyl group here. Okay, so this environment here is different than this, which makes these 2 not equivalent. Again, they're not going to be this difficult, but this sort of helps you sort of think about this. Okay, there's a lot of these sorts of things in the homework. Okay, because you can, but again, these are the steps you need to follow, sort of over and over and over again. Okay, so be careful. There's a little bit of nuance in these things. Okay, they're not going to be this difficult most of the time. Okay, something like that. So, okay, so let's do another one. Okay. So here we go. So C5H. Oh, actually, I think I have this. Oh, okay. C5H10. Right, plus you can see a little bit better. Okay, so first thing we have to do, right? So with that, so DOU, right? When in doubt, do a DOU. Okay, so 2 times 5 plus 2, no nitrogens, right? So 0. No halides, 0. We do have 10 hydrogens, right? 2. Okay, so 10 plus 2, so 12 minus 10 over 2, right? So 2 over 2, 1. Okay, so there we go. So we have 1 degree of saturation, right? So we don't know anything yet, right? Okay, so what do we know so far? Okay, so we know that. Okay, so this one here, so we can look at these chemical shifts, right? Stuff like that. So they're pretty far upfield, right? So this one here, right, so you look at this and hey, okay, so these guys here, when it's run 1, it's pretty much just going to be just like a, this is just going to be like a CC, right? So CH next to another C. Not too bad, okay? These guys here, if you notice, right, it could be here, okay? The other thing it could be is next to a ketone, okay? So the methyl ketone, so if you're next to a ketone, one away from a ketone, you're also here, okay? So that's something to keep in mind, right? So we can be next to a double bond, right? You can be next to this. The other thing, right, might be close enough to be on an alcohol, right? You're sort of at the two, well, that's the hydrogen here. Here we go. If you're next to an ether, right? So a carbon that has an oxygen on it, right? It's 3.3 to 4.5, right? So like that. So it's probably pretty far away from this. So it's probably not that. Okay. So you could have a alkene and that. I guess you could have a ring too. Stuff like that. That's another thing to think about. Stuff like that. So, but that one here, we have to keep an eye on what's going on here. Okay. So that's all I'm saying. Stuff like that. So, stuff like that. So it's probably not a C. It's probably not a double bond, right? Because we don't have, right. So it's not a CC double bond, right? For that, right? Because we don't have them in the right position, right? It would need to be within this 4.5 to 6.5, and we're not seeing that. Okay, so it could be a ring, could be something else. Okay, or because the other something else could be next to like a ketone or something like that. Okay, okay, so get the information that you can. Okay, so here we go. So okay, so we have a 6 hydrogen doublet. Okay, and so you have the equivalent of saying like a C6, right? We can't have 6 hydrogens on a carbon, right? The most we can probably have is really 3. You can't have 4, right? Because that's just ammonia. It's like or methane. It's not going to do you much good, right? So it's going to be something like that, right? So like that. So I just put that in quotes. So like that. So it's a doublet, right? So remember, it's n+1, right? So so doublet's equal to 2, right? So n has to be what? So we have to have a C. We have to have one neighboring hydrogen, right? Plus 1 to give the 2, right? So it's equivalent of a CH6 next to a CH. Okay. This one here, right? We have 3 hydrogen, right? So it's a CH3, right? What's next to it, right? N+1 is equal to singlet, which is 1, right? So N has to be nothing, right? You can't have any hydrogens on it. Okay, and then this guy here, right? This is, right, so a CH, right? But it's a septet. Okay, and so, right, so that means N equals 1 equals 7, right? Which means N is equal to this mythical CH6. Okay. Okay, the other thing is, you notice, is that there are 5 carbons and only 3 signals, right? So we have to be careful about what's going on next to this. Okay. Okay. So how are we going to deal with this CH6? Okay. So there has to be some sort of equivalency here. Okay. And so CH, right? We don't know how many carbons there are, but we know that there's 6 hydrogens. So we can either do it one of, right? So we can break this up into one of two ways, right? So we have a CH that is connected to, right? So we can either have a CH3 and a CH3, or we could do a CH, CH2, CH2, CH2. Okay? What's the problem with that? With this one, right? Here we can't have anything attached to it, right? Here we'd have to have things attached off of these CH2s, which would probably, and they'd have to be symmetrical, right? Because these all have to be equivalent to each other to give this the CH6 signal. So this is probably not going to be the way to go. This is going to be the way to go. Okay, and then this one here, right? Because this carbon has 3 bonds shown, right? So there has to be something attached there. Okay, so there has to be, do this in red, right? Right, it has to be something attached here. And that sort of makes sense what's going on here, right? So for this one here, right? So if we have a CH, right? We have a CH3, CH3, right? And then this will be attached to something, right? So these two are equivalent, right? But this one has to be on this side. You can't have any hydrogens on this side, right? Because otherwise you'd have a something of septets, right? So this one actually almost has to be connected to something that doesn't have any carbons on it, or not have any hydrogens on it, okay? Because otherwise this guy would be a neighbor, and it would split again, right? Stuff like that. So you would get the septet from here, and you get, like, if this was a CH, you have a doublet of septets. So you would be a CH, and the septets from the 6. So we have to be careful, right? So there's going to be something here, right? But then we also know that we also have this component here, right? A CH3 next to just a carbon with no hydrogens on it, okay? And so, aha, here we go. 1, 2, 3, 4. But if these two guys are the same, we could connect it like this. Okay, 1, 2, 3, 4, 5. 5 hydrogens, right? See, 3, 6, 7, 10. There's our 10, right? So where's the oxygen going to go? Well, these guys, these carbons, this carbon, this carbon, this carbon, this carbon, all have their 4 bonds. This one only has 2. So this is the only thing available, right? So we could have an oxygen here, right? Well, how are we going to do this? Well, hey, how about we just make that into a double bond? That takes care of our degree of unsaturation, right? We have the degree of unsaturation of 1. Well, there's a pi bond there. Okay. Now, does this make sense to the chemical shift information, right? So these guys here, these CH3s, right? They're just connected to a regular carbon. Okay. So they're going to be, right? So they're going to be really low or really upfield, right? You know, between half and 1.3, something like that. So yep, that's right where it needs to be. These guys here are the equivalent of being, right? So those would be, they say methyl ketone, right? But basically what it's saying is, right, a carbon next to a ketone, right? Well, that comes 2 and 2.4, 1.3, or 2.1, 2.43. Well, yeah, that makes sense, right? So like that. So we have these equivalents, right? So we now have 3 sigmas, right? Because we have this equivalent here. Okay, so we have this equivalent hydrogens, this equivalent hydrogen, and that one, right? So this one doesn't have any hydrogens on it, so that's not going to give any signals, right? So 1, 2, 3. Okay, so here's this is the only way that we can do this that makes sense with the information given. Okay, so by that, so we need to put all of this information together. Okay, so there we go. Okay, it's a lot of information, right? Since this was a long chapter, stuff like that. So the best thing to do is to just do the homework, stuff like that. So I remember when it clicked. I was an undergrad, eating lunch before physics class, doing the homework, and it clicked. Okay, so by that, so this the only way that you guys can do this is to do this over and over again, and just see the patterns for how you do the problems, right? So we talk about do the DOU, break out, you know, sort of see what the chemical shift information is telling you. Can it tell you anything? What do the integrations tell you? You know, what does the splitting? Yeah, so this will tell you what's you know, how many hydrogens are on that carbon typically, except for that one we did before, stuff like that. But what did the neighbors look like, right? Stuff like that. And so from all of that, you should be able to put everything together. And there's only going to be one solution for these things. Okay, that makes sense with all of this information. Okay, so with that, so do this over and over again, draw it out, right? There's plenty of room on the paper to do these things. Start working on the homework. And certainly if you're having problems, come see me. So good luck.